Today we're going to be talking about how to use calculus to find the area between curves. There's a couple of basic types of examples we'll look at, and then we'll move into some of the more challenging things. So just remember the very first startup from our Calc 1. If we have any two curves and we want to find the area that's between these two curves, so this is our goal. Find this area in between here. So if the first curve is f and the second curve is g, remember that the integral of f at x from a to b gets me the area below the curve. So if I integrate f, that will give me the area below f. Well, if I want the area between f and g, I just need to subtract off the stuff that's underneath g. So really what we're looking at is f minus g. Integral of f at x minus g at x. And in the book and in most of the examples, you're going to instead see that written as integral of f at x minus g at x dx. So, notice that at least in this example, and we'll actually see that in all situations, this is going to be the top curve minus the bottom curve. Top minus bottom will give me the area that's between the two curves. So let's just look at why that's true, regardless of where those curves are situated. So we'll do this with some real curves and some differently placed curves along the axes. All right, so suppose that we have e to the x is our first curve, and the second curve will be negative x squared minus 1. So a parabola that opens down 1 unit below the x-axis. Our goal is to find this area, let's say from negative 2 to 2. So that's what we want to do. Find that area. Now remember from the previous generic looking situation, we took the top curve minus the bottom curve. But in the picture that I had drawn, both the curves were above the x-axis. And this is a little bit different. In this case, we have above the x-axis and we have below the x-axis. So we want to think about if that's going to change our strategy. Well, let's just think about that for a second. All right, if I took the integral of e to the x from negative 2 to 2, that's going to get me this area right here in the red. If I find the area, the integral from minus 2 to 2 of the bottom curve, negative x squared minus 1, what does that get me? Well, the issue here is that this gets me the area, but since the curve is below the x-axis, it actually gets me the negative area. This integral will evaluate to a negative number. The magnitude, right, how big that number is the area, but it is a negative number. So what am I actually going to need to do in order to get these two things, to get me the total area that's between the two? Since this is a negative number, I actually want the positive version of that number, so really I need to subtract this. Because if I took this minus this, right, this is already a negative, minus a negative makes the positive version, add the two up gets me the total area. So in the end, even though this is above the x-axis and this is below the x-axis, we still have integral of e to the x minus negative x squared minus 1 from minus 2 to 2. This is always going to be the case. To find the area between the two curves, we'll set up an integral, top curve minus bottom curve. Top minus bottom, no matter where they are. Even if they were both below the x-axis, it would still be top curve minus bottom curve. Okay, now, a couple of things can make it a little bit harder. We can have a situation where we're not told exactly what the limits of integration are. Suppose that this parabola is x squared plus 4, and this parabola is so negative x squared plus 4, so that it's opening down. So this parabola will be shifted over to 1, negative 2. Let's say that this is the point 1, negative 2, which means that it's x minus 1 to shift it right, squared, and then minus 2 to make my parabola. If we remember how we create parabolas, right? So this is the vertex, shifted to the right, and then down 2 units. So these are my two parabolas. My goal is still to find this area between these curves. Okay, remember, top curve minus bottom curve. And that part is easy. The top curve is this parabola that opens down. The bottom curve is the parabola that opens up. The issue is finding these 2 points where we have to stop, the limits of integration. And so if we're not given the limits of integration, what we have to do is actually set the 2 curves equal to each other so we can find the intersection points. So we want the intersection points. So we need x minus 1 squared minus 2 is equal to negative x squared plus 4. We'll expand this out. X squared minus 2x plus 1 minus 2, negative x squared plus 4. We'll bring everything over to the left. So that makes 2x squared. So that's minus 2x. That's negative 1, and then minus 4 makes negative 5, all equal to 0. And then we need to apply our quadratic formula in order to get the points of intersection here. So let's apply the quadratic formula. We get negative b plus or minus the square root of b squared minus 4ac. So that's 8 times 5 is 40. That will be minus negative 40, so that makes plus 40. All over 2a. 2 plus or minus the square root of 44 over 4, which is 2 plus or minus the square root of 4 times 11, which makes 2 root 11 over 4, which is 1 plus or minus the square root of 11 over 2. So those are our 2 intersection points for the curve. Finally, we just need to set up our integration. Top curve minus bottom curve. The top curve was, remember that we had this type of situation. Negative x squared plus 4, and this one was x minus 1 squared minus 2. Okay, so top curve minus bottom curve is x minus 1 squared minus 2 minus, don't forget parentheses here, negative x squared plus 4, all evaluated from the limits of integration. So that the bottom one will be the left-hand one, which is the minus sign, 1 minus root 11 over 2, and the top will be the other limit of integration, 1 plus root 11 over 2. And it looks a little complicated, but it's an easy integration if we need to do it. We will just FOIL everything out, and then they're all just polynomials, which are about as simple as possible to integrate. Okay, so another type of problem which makes things a little bit harder. Okay, so let's look at another situation which can lead to a bit more trouble. So here's what we're looking at. Suppose that this is a parabola, but it's on its side now, which means rather than y equals, we actually have x equals. And this is a line which we can write as y is equal to 7 minus x. Okay, so our goal is to find this area. Here's the issue. Here's the problem with this. If we use the strategy that we were talking about before, top minus bottom, the problem is that right in this little area right in here, the top curve is the parabola, but so is the bottom curve. And so if we were to look right here, the top curve is the top half of the parabola, the bottom curve is the bottom half of the parabola, whereas over here, the top curve is the line and the bottom curve is the parabola. Which means that if we want to use the strategy that we were looking at before, we'd have to break it up into two different pieces. We'd have to find this intersection point, which is fine, we'll probably have to do that anyway, and then we'd have to make two separate integrals, because top curve and bottom curve are different at different points along the region. Now, if we are a little bit clever and turn our heads to the side, we can notice that if we were to think about this sideways, then this curve and this curve are always one above the other. So again, when we think top minus bottom, it's really positive y down to negative y. So if we were to turn our head sideways, that really corresponds to changing our variable. Rather than x is the variable, we're thinking about y is the variable. And if y is the variable, that means we can solve for x, which we've already done here. So in the old case, we were looking at positive y to negative y for top and bottom. Now we'll be looking at positive x towards negative x. And so we're actually not going to use these vertical lines. We're instead going to move the other direction. And if we move the other direction horizontally, notice that the top curve is the line, the bottom curve is the parabola, and that's true across the entire region. It doesn't matter where we are. We don't have two separate regions where one is the top, one is the bottom, and things switch around. It's always line over parabola across the entire region. And so that's actually what we want to do. We want to, instead of thinking about x as the variable, we're going to think about y as the variable, which means that we solve for x. And if we take this one and solve for x, then that becomes x is equal to 7 minus y. So now we have both of our curves solved for x, so that y is the variable. We need to still find the intersection points so that we can figure out what our limits are. But now the intersection points are going to be in terms of y rather than x, since y is our variable. And so let's do that. If we've set these two equal, and that gives us y minus 4 squared over 2 is equal to 7 minus y. So that's y squared minus 8y plus 16 all over 2 is 7 minus y. Multiply through this by 2. Y squared minus 8y plus 16 is 14 minus 2y. Bring everything to the left. Y squared, that makes plus 2y, so that's minus 6y minus 2 is equal to 0. Now, again, we just need to use the quadratic formula. There's no nice way of factoring this here because there's no way to make this 6 out of all of these numbers. So if we use our quadratic formula, let me just save the curves. So we have this curve and we have x equals to 7 minus y. Those are our two curves. If we use the quadratic formula, we get negative b plus or minus square root of b squared minus 4ac. Minus makes a plus, so that's plus 8 all over 2a, which is 2. 6 plus or minus square root of 44 over 2. 44 is 4 times 11 as before, so that's 2 root 11. So that's 6 plus or minus 2 root 11 over 2, which is 3 plus or minus root 11. Those are our two intersection points. Notice that these are y, because our original equation had y. These are y equal. So those are not the x coordinates, those are the y coordinates. So this bottom coordinate is the negative y value. So that's at 3 minus root 11, and this one is at 3 plus root 11. And so now we're in a position to write down the integration that will give us the area. Top curve minus bottom curve. Again, that's positive to negative. Y is our variable, so we're integrating with respect to y. So that's y equals 3 minus root 11 to 3 plus root 11. Top curve is the line, which is x is equal to 7 minus y, minus the bottom curve, and the bottom curve is the parabola, which is given right here. All right, top curve minus bottom curve. Y is the variable, so everywhere we see y. And this is the integral that will give us the required area. Now, that is the basic strategy for most of these problems. We need the intersection point, and we look at top curve minus bottom curve. Sometimes it's with respect to x, sometimes it's with respect to y. Let's just take a few minutes and end by talking about what types of regions make sense to use x as the variable and what type of regions make sense to use y as the variable. And some types of regions will make sense to use either. But let's start with x. That's what we're used to. Okay, so if my region is something like this, really comes down to the following point. If I can make a vertical line where the top curve and the bottom curve are always the same, no matter where I make my vertical line, then I'm going to be using x. Right? Because if I'm making a vertical line, we're thinking about shifting the vertical line across the region. If I'm shifting the vertical line, that actually means that I'm moving it horizontally. And so the vertical line is what we're looking at, and that's actually the variable. We're moving the vertical line in the x direction. So if I can take a vertical line, move it through the region, and it's always top curve and bottom curve that don't change, then that's when we're going to use x. Right? A vertical line so we're going to use x if a vertical line gives the same top and bottom regardless of where we are. So if a vertical line gets top curve and bottom curve, so the vertical line here, top curve is the same, bottom curve is the same, no matter where we make that vertical line. And so a good indication will be if my endpoints are vertical lines. And if the endpoints are vertical lines like we have here, then this is x equals something to x equals something. If that's telling us that x is the variable, and so that's why we're using x. That doesn't have to be the case, as we saw with the previous one, but this is the bunch line. So when do we use y? And exactly the opposite. Right, so we use y if a horizontal line gives the same top and bottom regardless of where the position is. Again, let's just look at the one that we were just doing, right, and talk about why that's true. Right, so a horizontal line now, top and bottom, top and bottom, top and bottom, top and bottom, no matter where we are, the top and bottom are the same. And so that's when we're going to have to use the y. It can happen in other situations as well. So here's a couple of other examples. Most of the time it's when we don't have a function, but we instead have a function that's turned on its side. That's how we're going to get to those types of situations. Right? So there's a function that's turned on its side. And again, a parabola that's turned on its side, if we want to find this area right in here, I would definitely not want to look in terms of x, because top curve and bottom curve change all over the place. Right here it's a horizontal line, and then this sideways parabola. We have this wavy thing over here. It changes all over the place. But if instead we're looking in the other direction, if we're using a horizontal line, and these are bounded by a horizontal line, so we should be thinking y equals. And in that case, no matter where we move through the curve, the top curve and the bottom curve will not change. Top curve, bottom curve, top curve, bottom curve. So essentially, if we turn our head 90 degrees and things look like what we're used to, that's when we're using y. And in that case, we have to take all of our equations, solve for x, so that y is the variable, and proceed from there. Okay, and that's what we got for area between two curves. I'll see you next time.